In this example, we have here a circuit, and then we're going to find the current in the resistor RL, so the current that flows here. All the network shown, so this is our network or this is our circuit. So we're going to use the Kirchhoff's law. So this is the KVL and then the KCL. So here, we have two power sources. Our first power source or voltage source is 24 volts, and then the second one is the 26 volts. So if you're going to use the Kirchhoff's law, it, I think we must know what is the KCL or the Kirchhoff's current law, and then the KVL or the Kirchhoff's voltage law. First, the KCL or the Kirchhoff's current law, we know that in your module it's stated there that it is the algebraic sum of the currents using and leave the current entering and leaving a node is zero. So in KCL, wait, in KCL, it's stated that the algebraic sum of the currents entering and leaving a node is zero, and we know that we have here a node. So this point is a node. Okay, so this is a node, and then for example, if we have so this is just an example. So this is just an example. If we have a current that enters here, let's say this is I1, and then we have also current that enters in this node. This is our I2, and then we have also a current that flows that enters the node. Okay, so this is just an assumption. So if we have a current here, so we have a node here, so this is our node. Okay, so we have three currents, I1, I sub 2, and then I sub 3. So assuming that the current is enters in the node, so this is stated here that or let's say that um, uh, the current that enters in the node, let's say that it is a positive, the current is positive, and then if it is leaves the node, this is a negative. So let's try to so let's say our I sub 3 is leaving the node. Okay, so if we have like this, so how are we going to find its equation? So as stated in the KCL or the Kirchhoff's current law, it is again the algebraic sum of the currents entering and leaving a node is zero. So again, the current that enters a node is positive and the current that leaving the node is a negative. So at this point, we know that I sub 1 and I sub 2, they are they enters in the node. So we can say that this is positive I sub 1, and then plus uh, positive I sub 2, and then also, so what will be the sign for our I sub 3? Since the I sub 3 or the current, our third source, I mean the third current or I sub 3 is leaving the node, so we can say that this is negative. This should be equal to 0. And now this will serve our equation. Now, for KVL, for our KVL, we have uh, we, the in order for the algebraic sign convention used in KVL, we must note or remind ourselves the following. So if the loop enters on negative terminal and leaves positive terminal, so let's say we have a voltage source like this. Okay, so if your loop is going like this, your loop, we know that this terminal is negative, and this terminal is positive. Okay, so if the loop enters, so it enters in a negative terminal and it leaves a positive terminal, so it enters in negative terminal and leaves in positive terminal, our voltage source is positive. Okay, so the loop, if the loop enters, if the loop enters a positive terminal and leaves negative terminal, then we could say that this is, so if we have a voltage terminal like this, yeah, so if your loop is like this, it goes like this, so we have a positive here, negative, so it enters in a positive terminal and leaves in a negative terminal, so this voltage source is this, this is negative V. So at this point, so kung sa Tagalog pa, kung saan siya lalabas, anong sign ang lalabasan niya, that will be the sign that you will be using for the voltage. So here, lumabas siya sa positive terminal, your voltage source is positive. So since here lumabas siya sa negative terminal, then we could say that this is a negative voltage. So, and then for the low, for the voltage drop, so for the voltage drop like this, so if we have a voltage drop, let's say, yeah. Okay, so what will be the voltage drop here? How are we going to know the sign for the voltage drop? So the voltage drop for here, so let's say the voltage drop for let's say this load. So uh, loop has the same direction as the current on the resistor. So if your loop has the same direction as the current on the resistor, then if your loop is goes like this and then the current is the same, yes, so we could say that your voltage drop for here, you're going to use the negative sign. Okay, negative sign. But if the loop has an opposite direction as the current on the source, so if the loop is opposite direction as the current in the source, so if the loop is going like this, then you can have a positive voltage. So that's how you are going to interpret or analyze for a particular circuit using Kirchhoff's law. So, okay, so let me erase this one. Okay, so in our problem, we have, so now let's proceed to our first example. So we are going to find the current in the resistor R sub L. So here, first we're going to determine what would be the sign for our voltage source. Okay, so to know the sign, so if we have so this one, the smaller one, this is our negative side, and this is our positive terminal. This is our negative terminal, and this is our positive terminal. So at this point, we can use, or we can have two loops. So our first loop using KZL, so we have a loop like this, and then also if a loop goes like this. So this is our first loop, this is our second loop. So now, how are we going to apply for the KZL or the Kirchhoff's law, Kirchhoff's current law? So at this point, this is, by inspection, this should be our node. Yes, this is our node. So if our loop is going there, our first loop is going there. So we could say that the current is also, so the current also flows from negative to positive, so it also flows like this. So since this is our voltage source from negative to positive, so that's the one how a current flows, so it flows go there. So therefore our current is, it flows there. So here is our I sub 1. So just observe. So this is for, so the current that flows, the direction of the current that flows um in R sub 1, which is 0.4 ohms, will be parallel for the our loops. So 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 this is a 1, and then for the current that will flows in our R sub 2, so it is parallel also for our loop here. So this is our I sub 2. Yeah. So and then what would be the current that flows for our R sub L? So by inspection, we know that the I sub 1 already enters the node, and then our I sub 2 is also, it enters the nodes, and then obviously it is impossible for R sub L that it also enters the node. Can't you imagine that wala siyang opposite, diba? So this is impossible. So in reality, if this is already enters the node, this already enters the node, the rest, the other one, it leaves the node. So therefore, our R sub L, the direction for the current for our R sub L is leaving the node. So at this point, we can now use the KCL. So applying the current Kirchhoff's law, we could say that our I sub 1, this is positive. The one that enters the node is a positive current, and then plus I sub 2, and then we have, since our I sub L is it leaves the node, we can say that this is a negative I sub L. And then as stated in the Kirchhoff's current law, that it is the algebraic sum of the current, and then it is equal to 0. So this will serve as our first equation, equation number 1. Now, since we have three unknowns, so at this point, let's say we are going to find the current for our R sub L. We will be also trying to solve for the current for the our I sub 1, and then for the current that flows for our R sub 2. So therefore, we have three unknowns, and then since we have three unknowns, we must have three equations. So in order to solve for three unknowns, we need three equations. So this is already our first equation. Therefore, we must have another another equation. So how to solve or how to find the equation? We just simply use the KVL, or the Kirchhoff's voltage law. So at this point, we can provide two loops. So this we already draw, and it represent like this. So this is our first loop. So now to at our first loop, I mean our first loop. So just focus in here. So just neglect this one. Just focus in the loop. So it's just like a single path. We will be, so focus in here, our first loop. So do not, so just cover this one. So just focus here, our loop here. So just neglect first this one. So when you focus here, and then we can find out the first equation using our first law, using the Kirchhoff's voltage law. So here, so let us now apply the KVL, the principles that I have discussed earlier about the KVL. So kung saan ka lalabas, yan ang sign ng voltage source mo. So here, so the sign for our E sub 1. Since you enters in negative and then you leave at positive terminal, then we could say that lumabas siya sa positive terminal, then that will be a positive E sub 1. Okay, now, second, since the our I sub 1 and the loop, they are parallel with each other, I mean they are in just the same direction, then we could say that the direction or the sign for our current is negative. So this should be a negative. Okay, let's say this is a D sub 1, right? This is our V sub 1. So our E sub 1, this will be our power source, and V sub 1, this should be the voltage for our voltage drop. This is the voltage drop for our R sub 1 load. So now next is, and then for our I sub L, that's the direction. So again, our I sub 1, the voltage drop here, it is negative because the current and the loop is the same in direction, right? And then uh, for our I sub L, does the loop here and the current, I mean the direction of the current is the same? Yes, it is the same. So this is a negative. I sub L equals 0. So this is already our equation number 3 that we will be using. So this is not yet the final equation number 3. And then using the loop for our second loop, so here, so if you're going to have a loop here, so it goes like this. So just neglect this one. So do not focus here. Just focus on our second loop. So in this loop we will be only involving the voltage source, our the voltage drop here, and the voltage drop for our I sub L. I mean for our R sub L. So just neglect the our E sub 1 and R sub 1. Just focus in here. So in order for to find the another equation for this one, okay, so I think there's something wrong here. This is not this is not our equation number 3. This should be our equation number 2. Okay, now next, so in here we use the loop here. It goes like this. So we enters in negative and we leaves in positive, and then lumabas siya sa positive, then our sign would be positive. So this will be positive E sub 2. Okay, and then what would be the sign for the R sub 2? The voltage drop here, what would be its sign? So again, as one of the principle for the KVL, if the direction of the current here and then the loop is the same, then it is negative. If it opposes to the loop, then it is positive. So since the current is going there, and then the loop is in the same direction with the current, and we could say that this is already a negative voltage drop. This is our negative, so this is negative V sub 2. And then for our I sub L, its sign is also negative because it is in the same direction. The current of our R sub L and then the loop is in the same direction. So this is also a negative V sub L. Equate to 0. And this will serve our equation number 3. So at this point, your first step, in order to solve for the Kirchhoff's law, first step is you are going to analyze the problem and identify what will be the power sources, what would be the resistances. So and then you're going to identify the node where the node, and then next is for the current, the direction for the current for the loop, and then the direction for each current. So current for the current for our R sub 1, what will be the direction for our R sub 2, the current that flows in E sub 1, for the current that flows in E sub 2, and then for our R sub L. So after identifying all the direction of the currents, now is using the KCL law. And then we are going to use the KZL. So just focus on its principle that since this is a Kirchhoff's current law, and we are going to use just all the currents. So KVL, and in KZL law, we are just only involving currents, and then again KVL, we are only involving the voltages. So just see its comparison. So now next step is, so after identifying the equations to be used in this kind of problem or in Kirchhoff's law. So for our equation number 2, now we can expand this one since we cannot find uh, so if we will be using this one, there is no distinct variable. So here we know that E sub 1 is already given. So this is E sub 1 for our equation number 2. This is 24 volts minus. So for our V sub 1, the voltage drop across our R sub 1. So we could say that this is already uh, we know that the formula for to find the voltage it is equal to current times resistance. So this is current sub 1 times resistance sub 1. Okay, so take note that the current here is the same as there. Then for our what would be the so this is also the I sub L, the current that flows in the R sub L, and then times the R sub L equate to 0. Now this is already our equation number 2. Or if we can, if we rewrite this one, so okay, so if we have a this is if we transpose is negative 24, and then if we're going to divide all side by negative, so we can have negative sign for all. So here it is. I mean positive sign. So positive. So positive. So yan. So this will be our equation number 2. Yan. So, may kulang pa pala. So we are just needing to substitute for the value of the resistances. Okay, so our I sub 1 is times the current, our R sub 1 is 0.4, and then I sub L natin is we have I sub L times 0.8 ohms, and then equals to 24. So this is now our equation number 2. So this is our equation number 2 again. So our equation number 2, I sub 0.4 times I sub 1 plus I sub L 0.8 times I sub L and equals to 24. So now next is to solve for the for our equation number 3. So we are going to derive. So for in this equation, next is we need to find its E sub 2. We know that this is negative 24. Okay, laki siya. So minus our V sub 2. So this is our V sub 2 is 0.4. So I sub 2 0.4 minus V sub L natin is 0.8. 0.8 I sub L equals to 0. Okay, so if we are going to, so we have already an equation like this. So now is to solve for, so now is to derive. So if we are going to transpose the positive 24 in the right side, so we have a negative 24, and then if we divide all side by negative, we can have a positive sign for all terms. So therefore, to solve for our, to derive our equation number 3, we have I sub 2 times 0.4 plus I sub L times 0.8 equals positive 24. This is 26, sorry. So this is 26. Okay. So this is our equation number 3. Okay, so if we have, now we already an equation number 3. This is our equation number 2. And then this is our equation number 1. So using your calculator, or if you're going to use any method using to find the 3 unknowns and 3 equations, we find the 3 unknowns using these 3 equations. So it depends on your how you know to solve this kind of equations. You can use the algebraic elimination, substitution, or etc. So but in this equation, this is already a correct equation. So equation number 1, equation number 2, equation number 3. So the final answer, our I sub 1, sorry. So our I sub 1 here. So overall, if you're going to solve this one correctly, or certain solution, so R sub 1, the current that flows here, it is equal to, this is 10 amperes. And then the current that flows in our I sub R sub 2 here is, this is equal to 15 amperes. And for our current, for our R sub L, this is equal to 25 amperes. So that's just and how to solve this kind of easy circuit using Kirchhoff's law. And again, just a reminder that we have such numerous methods or techniques in order to solve for this kind of circuit. So there is also a Maxwell mesh method. You can solve this one, and you can encounter this one in your DC circuit 1 next semester. And then we have a nodal mode method, superposition theorem, and etc. So again, overall, our this is our final answer. So if you have a question, just drop your question in the comment box below the comment section, and then I can answer it later. Thank you.